process. So you have only information before and after the gas enters the pipe and leaves. Means when the gas enters this porous region or constriction, before that you know the property, and once it comes out, then you know the properties. This process is called throttling process, and under the approximation of no work, under this condition, no work and no heat transfer. Okay, and if we ignore delta K, that is change in microscopic kinetic energy 0 and change in microscopic potential energy 0, under these assumptions, we will see that, and in fact, you can figure out from the energy equation for flow process that we achieve this. So that's why we call it isenthalpic. That doesn't mean that it's a equilibrium process. Isenthalpic means before and after enthalpies are same. Okay. Now, what is the effect? So first of all, how we do this? One more point. What depending on what is the exit pressure. Okay, depending on at the exit. So let's say this is inlet, the pressure at which you maintain before the gas enters into the porous plug, and this is P exit, which you maintain at the outlet. So depending on what is the exit pressure, sometimes T is less than Ti, sometimes T is greater than Ti. If this we got that T exit is less than Ti, this is a cooling effect, cooling of gas, and it is very advantageous for many practical purposes. And the most important process in this modern era is that refrigeration process. Another important application is liquefaction of gas. Liquefaction of gas. Okay. Why we can apply first law? Because we never said that first law is valid for a reversible process. Reversibility comes when because of this formula of work done, W is equal to integral P dV. But here there is no work transfer. So of course you can apply first law of thermodynamics, the rate equation, energy equation in terms of rate. So this we have under this approximation. Now there was a doubt in the previous class, and maybe we can interact with let's say Vatsal. No, Varun. Yes, Varun. You are there, right?
Yes, sir.
Yeah, Varun. So there was a doubt raised by a student that many times we have this confusion DH equals to CPDT. That's what he asked. That's a DH is 0 in this process, as we are saying it's isenthalpic process. So then DT should be 0, no temperature change. Then why you are saying that this temperature, there is a temperature change, either temperature can increase or decrease. So would you like to comment where is the catch in this expression? What is wrong with? And there's nothing wrong, but how you can justify, or how you can convince, or how you can explain that person who raised this doubt? Any thought?
So maybe the enthalpy at the beginning and the end there's no change, but in between it can change. So that's why
That's fine. But that's fine. But H is a state function.
Sir,
Right?
hello, sir.
Yes.
So like it is for the thing that you mentioned is for an ideal gas, but we are considering real gas.
True, but then I need some more inputs from you. That's true. That's a starting statement just to convince you, but more scientific and more precise answer.
So this is just a way to enthalpy. Like we can calculate enthalpy by taking the system at constant pressure, but it is not like enthalpy is always at constant pressure.
No, but then his point is that H is a state function, so it doesn't matter how you do the process, right?
Sir, for a real gas, the enthalpy depends on the temperature and volume.
Very good. Pressure. That's fine. Once you any two variables, because third one is interlinked with equation of state, right? Very good. So remember that in general, H is function of both T and P. And the correct definition of this is this: dou H by dou T at constant P is Cp. Okay, now you can only write is dH equals to Cp dt if this H is only function of T. That is only true for real ideal gas. You can check. That is only true for ideal gas. That H is only function of temperature. Okay. Or in other way, we should say this way. This is not correct. Rather than I should say this way. That the correct way to say it is that in case of ideal gas, Cp only depends on temperature. That is the correct way. Cp only depends on temperature. But if we go to real gas, that is not the scenario. In fact, when we'll discuss thermodynamic potentials, we will see this formulation. That the full formula of enthalpy change as H is function of both T and P is this. So apart from this term, we have some other term also. Okay, where beta is isothermal expansion coefficient. We'll see what it is. So the bottom line is that this is only true for ideal gases. dH equal to Cp dt. Okay, in that case, so for ideal gas, you can say for ideal gas, H is only function of temperature. Can anyone prove that? It's very quick. H equals to U plus PV. And what is PV for ideal gas? If you take specific volume, RT, right? So H is only function of T. So in that case, you can write dH equal to Cp dt. And that's why, can anyone guess for a real gas, what does mean by throttling process? Is there any change in temperature?
For real gas, yes. Cooling
Sorry,
down.
for ideal gas. Sorry. For ideal gas, no change.
No change.
So if you take ideal gas, there is no change in temperature because then H becomes only the function of temperature. It's not a function of pressure. So this is only valid for ideal gas when H is only function of T, as I already written that. But in general, for any real gas, this is valid. So it is possible that even keeping the enthalpy same, temperature can change, and that is all about throttling process. Now we will go to a very, you can say a very, renowned experiment, a very legendary experiment done by Joule and Thomson. It's called Joule-Thomson effect, which is nothing but to explain the throttling process. So let's go to that. So first we understood what is throttling. We today try to increase our pace. Now what is Joule-Thomson effect very quickly. How we do this experiment? So as I told you in Joule-Thomson experiment, at inlet you maintain some pressure, let's say Pi, and at outlet also. Okay. And you maintain this pressure, and how you can do that? By using this movable piston system. So how you'll do experimentally, that's a different issue. Once you're really interested, you can see that how we can maintain this pressure. So here we have a constriction. Here we have a porous plug. In both cases, what we are maintaining? That we are maintaining exit pressure at some pressure P, which is lesser than Pi. That's what we are maintaining in Joule-Thomson experiment. Okay. This is, you make sure it's adiabatic. So either you can cover it with adiabatic wall or you have to do it very fast. So another thing is adiabatic. No work transfer. There is no work. There is no shaft. There is no rotor. Okay. So Q0, Q dot 0, you can say WS dot 0. Fine. Now you note down the temperature also. You put two thermometer probes and you can put two pressure gauges to measure the pressure, that whether you are maintaining that pressure or not. If your pressure is not maintained at that P, E and Pi, then you play with these pistons so that you maintain these inlet and outlet pressures. Okay. So we have temperature also, Ti and TE. Okay. And then what you do in this experiment is as follows, so that you can understand this temperature pressure curve. Okay. The curve which you see here on the right hand side is curves created by this Joule-Thomson experiment. So what you do, if you take any curve in this experiment, when I say any curve means, let's say if you take this curve. So how we have created this curve? So what we have done, that we have maintained a exit pressure, let's say at PE1. So maintain the exit pressure at some given pressure PE1, which should be less than PI. Okay. And then or is it no, I think we are fixing, sorry. Fix your inlet temperature. So this is for a given inlet temperature PI. Okay. Yeah, no, it's fine. So you fix your inlet temperature. So PI is fixed. Okay. PI1. So each curve, it corresponds to a fixed inlet pressure. So fix your PI1. And then what you are going to do is as follows. In experiment, you will vary the exit pressure P exit for this given PI1. Okay. And you will measure the exit temperature. Inlet temperature is also fixed, by the way. This is also fixed. Huh? Fixed. This one and this one. Okay. And what we are playing with P. Okay. You are maintaining the exit pressure at different pressure and for the gas which is coming out. So you let's say you have some reading, some exit pressure, some exit pressure, some exit pressure, and then correspondingly you are measuring temperature also. Some temperature, some temperature, some temperature, some temperature, some temperature. And then you plot that T and P. So this is TE and this is PE. If you plot this P versus T data, you will get this violet curve. Okay. And in this process, what is happening? That enthalpy is constant, right? So this is for some enthalpy. Inlet enthalpy is equal to outlet enthalpy. So let's say H. Okay. H you can write as U at inlet 1 plus PI1 VI1, and that is equal to exit thing also. So H is going to be constant. So H will take some value. Let's say it H1. Let's say it H1. Okay. Fine. Then what you do, that you take another, you maintain this for another P inlet. So let's say PI2. So take some another curve. You can say PI 1, 2, 3, 4. So let me check that there is no mistake. It's a very serious experiment, so I may also get confused. Just let me check. But I'm not making any mistake. Fine, it's okay. Yeah. So this way again, you fix your inlet temperature at some pressure, PI4, let's say, and then you will play with the exit temperatures. So again, you will get the same kind of data for PI4 also. And then again, you plot it. This way, you draw this isenthalpic curve. So let's say this is for enthalpy H4. Okay. So first of all, this creation of curve is clear, Varun?
Yes, sir.
So what we are varying and what we are fixing?
We're fixing the initial pressure and like fixing the enthalpy, then the initial pressure, and then plotting it according to exit pressure.
You are fixing pressure since it's an in throttling, isenthalpy remains constant. So
we get P and T, and then we plot.
H is a function of PI1, and H is not going to change. So by default, H also remains constant for a given curve, right?
Yes. Yes.
And then for another curve, what you change?
You change PI.
You change PI. Okay, you got it. That's perfect. Now the experiment tells us that in some particular region, let's say from here to here, this curve looks non-monotonic. It passes through a maxima. Okay, and that point is called inversion point. Then that point is called inversion point. Okay. So what you see here, that before the inversion point for any curve, let's say if I choose this curve, before the inversion point, if you go, let's say left, okay, if you go left, when pressure is decreasing, temperature is also decreasing. When P is decreasing, T is decreasing. It means that the exit temperature is lesser than this Ti. Okay. So this is cooling effect. On the other hand, when you go to high pressure region, means when you go in this region here, what we see, when pressure increases, then temperature decreases. So if you come towards left, so let's say if I start from here for any curve, if I'll decrease the pressure from high pressure region for exit pressure, temperature will increase. You see, if I go from right to left, follow the green curve. If you go from right to left, what is happening? Pressure is decreasing, but exit pressure, but temperature is increasing. So it means gas is heating up. But when after a certain point, again when you lower down the pressure, temperature starts decreasing. That is cooling effect. So for a given enthalpy or for a given inlet pressure, there are two regimes. In one regime, if you decrease the pressure, gas will heat up. In other regime, if you decrease the pressure of exit pressure, then temperature will decrease. This region is called cooling region. This is for a gas at different enthalpies. Okay. If you take any curve, this is a curve of T and P. So now I will not mention T and P. It is understood that we are talking about exit pressure and exit temperature. What we can define is this. Mu Jt. This is called Joule-Thomson coefficient, which is nothing but dou T by dou P at constant H, which is nothing but exit. Okay. So for a given H, means for any curve, which is isenthalpic curve, we can define a coefficient which is called Joule-Thomson coefficient, which is nothing but the slope of this curve. So can anyone comment in cooling region, mu Jt is greater than 0 or less than 0?
Greater than 0.
Greater than 0, right? Because as P increases, T also increases. Okay, so mu Jt is for cooling region. Okay. So as you can see here also I have shown the various inversion point. So if you take any real gas and if you are maintaining the exit pressure in this cooling regime, then the effect will be that the gas which is coming out, it will cool down. Okay. If still you are confused, let me explain this way. One can think that, okay, fine, temperature T will decrease, but then why you are saying that T is less than Ti? So if you talk about the cooling, so let's talk it afresh. This page is fine. Let me open the new page, just a moment. Yeah. So you can, well, what we are observing that for cooling regime, what we observe that as PE decreases, T also decreases. That's fine. That we see here. Or we can say other way also that as P increases, T increases. So P is an increasing function of T. T is increasing function of T. One can ask me always that, sir, why you are claiming that T is less than Ti? Because when the moment you say cooling, this is cooling. So how you claim that? That this fine P and T are like it's a monotonical. I mean, it's an increasing function before this inversion point. But how you are claiming this? So it's a very simple. We have a very simple. Yes, Varun, you want to try? Why we are saying that? Not difficult, so you can give a try. Or wait, Varun. Wait. See, is this Somvik, you are there, no? Oh, Vivek. Let's talk to Vivek. I have never. Vivek, Surekha. Vivek. Vivek.
Yes, sir.
You want to give a try?
Sir, I am not able to
How we are
understand.
claiming this?
I don't know, sir.
No, I know you don't know. You have to try. So what we discussed, by the way, can you explain that before this? What question I asked? Then probably you can try. Just repeat the question. Which I'm trying to ask to the class. Yes, go ahead. Yes, Vivek.
Sir, I didn't listen that.
That's really makes me sad. Okay, don't do that.
Yes, sir.
I mean, this is not good. Vivek, see, we are in offline, in this online mode. If you don't cooperate, I mean, you know, you'll never learn. So, see, remember one thing for all of you. Don't think that whether it is applicable in your future job or not, or these are very temporary thoughts. See, the most important quality of a professional, that whatever is the current task, give your dedication. That's all. Being too much futuristic is also, it doesn't help. What helps is that you are committed to your current task. Okay. So keeping that in mind, my sincere request that if you are here, listen. Otherwise, you can leave the class. Very simple. No problem. I have no issue. No marks for attendance. I don't believe in that forcing someone that you learn. No. I don't believe in that concept. So if you're not interested, I will not mind. It's your choice. Because you are grown enough and we are in a system which is quite liberal. So it's your choice. Don't worry. Okay, Vivek, thank you. Yeah, so let me, okay, so let's come back to Varun. You want to give a try?
So maybe I think because if you said
so the hint is that think that it's isenthalpic process.
Yes, sir.
What is going to be constant? H exit and H. Right?
Yes, sir.
Yeah. And we know that H is function of T and P.
Yes, sir.
So if both are going to remain same, and if one is, so both are going to remain same, right?
Yes,
now what you are saying that let's say PI P, what we are saying that PI is greater than P, right?
Yes, sir.
And if you want to maintain this, what we have to do? That the only possibility that in cooling regime that this wait. So if we are claiming that H is same and temperature exit should be, so if I'm just okay. So where is the fault then? In order to claim this, sorry, you want to claim this, no?
Sir, I was thinking maybe like if the starting pressure is in the region of cooling, like if PI is in the region of cooling.
That's true. I'm just wondering, wait, that is this true always? Before that, just give me a moment. So if H is function of P and T, or there is something else that H is function of, I think beta, because if, according to this, how are you going to maintain? So H is U plus PV, right? And oh, I think that V will matter. I think this beta will matter.
Yes, sir. Because
otherwise we can't claim this.
It's a relationship.
Yeah, beta will there. So that relation is, so yeah, so we don't go into that. I think this is not the right moment. really we should wait, because it's not so easy process to explain mathematically. We have to take help of other relation also, like this here. So I think this is not the right time to explain that thing. Anyway, so what is happening? So so right now, anyway, we are claiming this, and let's say that we are claiming from the experiments. I'm not going into this. Probably we need some more thermodynamic mathematical input to prove this claim, but it happens in the cooling regime. That's all we can remember right now. Okay, but of course, one thing we can surely. So what I am leaving here, that how this claim is true. Right now I don't have answer, because the reason is that we haven't covered this derivation. So probably we can again discuss after this derivation. Okay, that how this claim is true. Those who are not clear what our confusion is, those who didn't understand, our confusion is that Pi is greater than P, Ti is greater than T, but still, and if we only assume that H is function of T and P, then Hi should be greater than He, but that's not true. Hi is remaining constant. So it means there is something else, and that something else is beta. So through this simple H is function of T and P, we cannot explain why cooling occurs mathematically. But I'm going to give you the molecular picture. Mathematically, I cannot explain right now because we haven't derived this relation. So we'll wait. But I can give you the molecular interpretation, that why sometimes cooling occurs and sometimes heating occurs. Okay. So let me explain that thing to you. Okay.
Hello, sir.
Yes.
Sir, can you tell if we are keeping Ti constant for this entire process?
For this entire process. Okay, let's see what happens.
Like for different curves, is Ti same?
For different curve, I think, yeah, we can maintain a Ti constant. Yes, we can change only Pi. Yes. But
Okay,
Ti,
so
I think it's not mentioned. I think this is for a given Ti. You are right. So you are saying that whatever this you have created, for all these curves, Ti is constant. Am I right? I think you are right. This I need to check. That's what you are trying to say?
yes, sir.
Yeah, I also think so.
So
That
for this, we
yeah.
need to like specify the starting point. Then we can say.
No. So starting point in the sense that you, what do you mean by starting point? We have to
Like
change.
we are in the cooling regime for a.
Okay. Let's go into that one by one. So first of all, let's talk about one curve. So first of all, for all the curves, in general for this curve, I think that input it is perfectly correct. I'll check in the book, but I think Ti is constant throughout for all curves, right? And then let's talk about one curve. So for a one curve, who was saying starting point? I'll follow your suggestion. Of course you are right, but just help me. So you are saying that for a given curve, the starting point will be Ti and Pi1, right?
Yes, sir.
Okay.
Yes, sir.
Yeah, so let's do it systematically. Pi1, and the moment we say Pi1, our H1 is also fixed, right? So this is for curve for a given H1. Now what we are saying, that H1 at inlet is going to be H1 same at outlet, right? It means you are saying Ui, of course, which is a function of Ti, plus Pi1 Vi1 is equal to, this is going to be, sorry, Ui1 I have to say, this is equal to, this is always going to Ui. So what we should write it? U exit 1, right? Plus P exit 1 plus V exit, into V exit 1. Okay. Now, as someone claimed that since throughout for all these curves, Ti has to be constant. So for each Ti, we'll create such many plots. This is not going to change. Am I right? Whoever said it, that in all such equations, Ui will be same, right?
Yes, sir.
Okay. Now, what is going to change is this UE1. Okay. And and for a given curve, what we are fixing is this fixed for isenthalpic curve. And that for given isenthalpic curve, we are playing with P. So this will vary, right? And this will vary, and of course this will also vary. This is function of this, and this is function of P exit, and that's what we are measuring. And what is happening in cooling region? That T is less than Ti. So right now, I don't think we have way to prove this. I don't think so, because a lot of information is in V. Okay.
So you just mentioned that internal energy will vary, but since from first law of thermodynamics, we know that there is no work happening and no heat exchange. So how can internal energy change?
I'm coming to that. That's what I said, that I have molecular interpretation, but mathematically it will take a lot of time to prove that. So give me rather than giving some time, when we'll do this derivation, that DH expression, probably we'll revisit to claim this effect. But I have what you asked, that molecular interpretation. I'm coming to that, why it is happening. Right, that's what you asked. Huh? Okay. So right now, yes.
Sir, you said that H1 equal to H2, right?
True.
So then if P exit is increasing, so that means that U exit should decrease, right? So that means temperature is decreasing.
Wait. P exit is decreasing, so why you cannot say that? You cannot say anything.
Sir, H is constant.
Oh, you are saying no, but what about the V?
Sir, for like simplification, if we consider V also constant.
Difficult. It's a specific volume. I mean,
like when we say that
let's say it's remain constant. Let's say, which is very difficult, but anyway. So,
sir, let's not think that's constant. If we say that H1 equal to H2,
fine.
So we say that PV is increasing because that's what we are doing in cooling region. Like PV is increasing, so like U should decrease to keep H constant. So that means temperature should decrease.
That is one. So you are then you are assuming that. Wait, you are saying this P exit, this pressure, this P exit you are maintaining at pressure lower than Pi. Is it always the case? I have to check the experiment. So what I claim that, is it that P exit is always less than Pi? I think no. Right? Let me see the experiment. That in the isenthalpic experiment, is it like we always maintain? If that is the case, then what you are saying is not. What you are saying is correct. This confusion I have, I overlooked this. Let me see if.
Sir, I did not get the point that for all the curves Ti should be constant.
Then you have two parameters.
Sir, but at inversion point Ti is equals to Te, na?
No. At inversion point, why Ti is equal to no, not at all. At inversion point, simply we are saying mu J T is 0, nothing else. Means the exit temperature will start decreasing with when you go left. The exit temperature will decrease when the P exit will decrease. Inversion point is see, inlet temperature is fixed. All we are playing with this outlet temperature. Are you getting my point? Hello?
No, sir.
Clear your doubt, and then we'll move. And then we'll come to this, that I am just not sure that this thing which I have mentioned, is it always correct or not? Or I mean, there is no such criteria. We fix P and we play with different P. That's what I think.
Sir?
Yeah.
Sir, if we consider that VE...
No, before that, Bhavna, before that, just first let me clarify his doubt. Who was asking? Just first to make sure that you understood the experiment. Otherwise, there is no point. Now, what you asked? Hello? Yes.
Sir, I could not get why Ti should be constant for all curves.
Why not? See, Acha, what is our experiment? What we are measuring here in this curve? Tell me. In this curve here, what we are measuring? What is our data point which we are noting down? TE and PE.
PE.
So we play with P and we measure TE, right? What we need to okay. So then, if you will vary TI and PI also, then how you will mark those curves? You can mark. It's an isenthalpic. In fact, see, the ultimately we are keeping constant H equals to. I'm coming to your point, and you will get convinced. We have to keep the enthalpy constant, right, for a given experiment. Okay, what's your name?
Yash.
Yes. So H is constant, right? Now I'm coming to your point, and you will be convinced. H, it's a, let's say if I write in terms of UI plus PIVI, right? Okay. One way to keep H constant is what? That so H is constant for a for H is constant for a given experiment, not for the curve. For curve also it is constant, right? Just a moment. For curve also it is constant. So if we vary the PI, can we keep the H constant? I think your point you are making a right. Let me see that if you want to keep the enthalpy constant, how we can do that. Is it like we have to vary the temperature also? Wait, guys. I think your point is valid. That why we are keeping Ti constant. So what is constant throughout this curve? H, right? Yes, that's what you are saying, right? That if H is constant throughout the curve, if you only vary P, I, then probably you are saying that we cannot maintain constant H, right? That's the point. We have to vary Ti. I think that's what you are trying to say, isn't it? Yes.
Yes, sir.
I think that's what you are saying. Yeah. Okay. I think your point is valid. Achha, anyone has any comment on this? Because I got his point. First you guys say, and then I'll tell that where again. Yeah, Bhavna, you're saying something. Yeah.
Sir, but here we are wearing PE, right? PI and TI are like fixed so that we get a fixed enthalpy. And then we are plotting PE and TE. So PE is changing, na?
That is also one. Oh, yeah, that is also one point. Right. Yeah. It's really. So your point is also valid. That since here, once we fixed our H at any point, then yeah, we are wearing P. So correct. Okay. Now I have a complete picture. Thank you guys with this discussion. Okay. Now let me again start this. Unless until we. Okay. So yes, you listen carefully because I think Bhavana made a very good point, and then I can. So we are for a given curve. Let's talk about for a given curve. H is UI plus PI VI. Thank you, Bhavna. Okay. Now what we are keeping constant is yes H. Right. For a given curve, H is constant. You agree?
Yes.
Let's say H1. Okay. So let's say I will not change the temperature. I am saying fix your TI. Fixed. So what is going to be get fixed? UI. Okay. UI is fixed. And what then what I am doing in my experiment? So if you take any curve, tell me what in this curve what we are measuring. This curve created how? Yes. T exit.
For different pressures, we are measuring T exit.
Right. Okay. So all you need to do that you play with this PI. So let's say first you choose any PI, any PI. Let's say PI1. So we'll get H1, right? Some enthalpy value H1. Are you getting my point? For a given experiment, let's say experiment 1. Experiment 1. Ti is fixed, of course. Then I set Pi1. This is fixed. And then what I am measuring? T as a function of P. I'll get this curve, right? Yes?
Yes, sir.
This is for H1. Now let's say if you want to do it for H2. Experiment 2. Let's say experiment 2. Again, I am fixed. Ti is at the same value, and pressure I am taking Pi2. So what will be my H2? Tell me. Yes. Yes. H2 will be. UI is same. UI is same.
UI plus Pi2.
So you'll get some curve for H2. So there is no problem. I was right. I mean, since there's so much discussion. So by fixing Ti also you can. I mean, if you fix your Ti, you'll get the same curve. I mean, you can generate this curve. You got the point. Now your point is also valid, but there exists a combination of other Ti and Pi where you can repeat these curves. I think that's what you're trying to say. So our point is also valid that even if you fix Ti, by varying Pi, you can generate this isenthalpic curve. You agree or not? Or no? Or still you are confused?
No, sir. I got the point.
You got the point, na? Yeah. So fix Ti, change Pi. So once you change the Pi, your H will change. For that given H, we are creating this T versus P. Then you can choose another. So let's say we choose Ti for one experiment. Ti experiment 1. You can choose Ti for experiment 2. And then again you vary this Pi1, Pi2. And it is possible that probably you can repeat some of these curves. Okay. So the bottom line is that you have to maintain a constant H. Okay. For a given isenthalpic curve. You can do it in a different way. One way is fixed. Don't change your Ti. Don't change your Ti. Only play with Pi. Fix your Pi. Measure T versus P. One experiment over. Then again, don't change your Ti. But take another Pi. So you have another H. And again vary T versus P. Okay. So I think this makes sense.
Sir,
yes.
I have a doubt. Hello, sir.
Yeah.
Yes, sir. Avilash this side. Sir, I was asking that if we are measuring the temperature and pressure at the exit point, then how is it changing? Meaning, is it with time?
No. So there is a catch. What I said you, we are maintaining the exit pressure. What we are measuring is the exit temperature.
Okay, sir. Okay, sir.
It's possible. That's why we are using. That's why I emphasize that you have to use this piston system, and there is a pressure gauge, a pressure meter. And if you see that, let's say P inlet, you are maintaining at 5 bar. Okay, and P outlet, you are maintaining at 1 bar. So let's say here is the marking 1. As soon as you see that the needle in your pressure meter is going deviating from that 1 bar reading, probably you will push the piston forward, or you have some inert gas. You will fill the inert gas so that pressure increases. So that is the experimental task, that how we'll maintain. But we are maintaining. So P is maintained. P is controlled by us. P is controlled by us. And what is what is not in our control is T. T is the effect. Is it clear?
Yes, I see. It is fine now.
Yeah. Okay. So I think we discussed a lot. Still, I have a doubt, guys, and I'm just sharing it with you. That the thing which I said, I don't know how to check. I will be very frank. I didn't check this. That I said that we are maintaining P exit less than P in I. I don't think it's always true. I don't remember, but I have to check the full detailed experiment, that whether it is always true or not. What do you guys think?
Sir, for this, I was saying that even if P exit is less than P inlet, we can still have a variation in volume. So if we exit...
that is true. That is true. But I'm just, as a query, I'm saying that is it that we are maintaining always, or that's not the case?
So it's given by definition that change in pressure is negative.
Sir, if exit...
that is a cooling effect. That's why I'm checking the Joule function experiment. That's why I also overlooked that it's a cooling.
Yes, so obviously move from high pressure regime to low pressure regime.
No, but you are always free to maintain. Yeah, that is also true. That is otherwise we won't be able to push. That is my point of confusion. That let me check.
Sir, we say that sometimes when expansion occurs, the gas cools down. That's what Joule-Thomson expansion is, right?
Yeah, true.
VE,
Sometimes cools down, sometimes heats up. So this is always true, right?
yes, sir. So VE has to be greater than VI.
Yeah. So that's what Joule-Thomson effect is true. That that sometimes cool down, sometimes heats up. Then in that case, still we haven't proved this claim mathematically. That the what we said, that how we can say that, how we can justify mathematically that sometimes Ti can be less than, sorry, sometimes T can be less than Ti and still H is same. So this we haven't proved mathematically. Okay, with this discussion, let me summarize all the important points so that we will not get confused, since your inputs were great from all of you. And that's why I always take teaching as a learning experience. I learned a lot of things from students. So anyway, because once it is, then you realize that, okay, this point I missed. Thank you. Okay, so let me first, one by one, we'll fix so that there should not be any confusion when you go through this topic. So, T inlet is fixed throughout. It's not a thumb rule, but just for sake of experiment, fixed for all curves. That's how I am doing experiment. Point number one. Then for a given curve, Pi is fixed. Okay. So if I say this is Pi1, then H1 is fixed. Okay. And again, so this is, you can say this is for this experiment for one curve. So if you take any curve, that's a curve for H1, it simply means it's a function of Pi and we are not changing Pi, and this is Pi1. Then when you take curve H2, again this is Pi2, but we are not changing this. That is point number one. Then again for a given curve, since let's say Pi1 you fix it, then what we are measuring is for this Pi1 and Pi inlet, P exit you are controlling. So this is your control parameter, controlled, and effect is TE. That is whole experiment. And then at the last, someone has cleared my confusion that it's a Joule-Thomson effects, and sometimes when gas expands cools down, and sometimes when gas expands it heats up. Another thing was very important comment, that since gas can always flow from high pressure to low pressure regime, so there should not be any confusion, and thanks for that point, that P exit is always less than P inlet, always in this experiment. Always. True. Okay. So this will be our master slide, just to summarize. Then what we said, that in case of cooling, so that we should know that what we didn't answer, so that we can come back. Cooling regime, in cooling regime, T exit is less than Ti. That's what we said. Now, what we are trying to figure out that why it happens mathematically, and what we said, that we are saying that H inlet is H exit. It means Ui plus Pi is equal to U exit plus V exit, V exit. Okay. Now, since U is only function of temperature, okay, we certainly know if we see these two quantities, UI and UE, we certainly know, say in cooling regime, we certainly know that UE is going to less than UI. Still, H, we can maintain the H, you know. So, what we are saying, I'm just summarizing it here. So, this is one slide, cooling regime. Let me, so what we are saying, P I is, let me write this way, Pi is greater than P, no doubt, always. Then we said in cooling regime what happens? Ti is greater than T. It's an isenthalpic process, so we are saying Hi is He. We certainly know from here that Ui is greater than Ue. Now you see that Ui is greater than Ue, and another thing we also know here that Pi is greater than P. Now if you see the definition of H, it's Ui plus Pi Vi, we are saying is greater than Ue plus P V. So you see why I said that we can't claim right now. This is greater than this, and this is greater than this, and still H is same. You know, in both components, in left hand side, Ui and Pi is greater than UEP. Still H is constant. It means there's a lot of information in this.
Sir, that is equal, right?
Oh, sorry, that is equal. I'm very sorry. I mean to say that you got the point, na? Sorry.
Sir, so if UI is greater than UE, then Pi Vi is less than PEV.
No, but Pi is greater than also PE, na? You are missing that point.
Yes, sir, but Pi Vi is less than PEV.
No, that's why I'm saying that the information is in Vi, and why I should say PV.
Yes, sir.
That's what I'm trying to do. That rather than make it complicated, we should be very clear that where that whole crux is there. This whole effect is on due to this V. You know, this change in specific volume, right? And that is related to what we know as beta, that or kappa. You can say compressibility or isothermal expansion coefficient. So that will come later, right? I made a point clear that rather than PV, we should say, because we know certainly that Pi is greater than PE, right? It's because it's expansion process, right? Yeah, who was the? I mean, yes, who was saying
yes,
PV?
sir. Yes, sir. Correct.
Yeah, just the name.
Sir, Soham.
Shubham. So yes, clear, right? That everything is in. So okay, so this is still question mark, and we will revisit this. I think now there should not be any confusion, because I also got confused, to be very frank, when too many things came, and you guys cleared that out. So that's the real purpose of class. Thanks. Okay, so now we know actually now how we can claim. So I don't know the mathematical answer, in the sense that we have to explore more when we see that relation. But of course, I can explain you how it is happening. See, your confusion can be that we know that this internal energy of exit gas, this UE, is lesser than UI in case of cooling, and sometimes it heats up. So how we can explain this? So let me explain you this way, and let me say, and then you can leave just 2-3 minutes. So that's why I put this this slide. See, what is the molecular interpretation of this? That if you see the gas, what we know as average molecular kinetic energy, right? So if you take the gas, there are two components. One is molecular kinetic energy. Okay, this corresponds to what? Which quantity this corresponds to, or which thermodynamic property? U, right? Do you think anything else is there in gases? Anyone? So this is this molecular. This is interaction, molecular interaction energy. So the correct word is. So if you take any gas, let me write it properly. That if you take any gas, we have molecular Ke plus molecular P. Sometimes this is also called as molecular interaction energy. Okay, now try to understand what is happening here. Now this molecular K is a manifestation of what?
Temperature.
Temperature. Okay. See, now what happens if we see any any Joule-Thomson isenthalpic curve TP. This is inversion point. What is happening that when you are in the low pressure regime, low pressure at exit, okay. So which is low pressure regime? Let's say here. This is low pressure regime. Low pressure. In low pressure regime, what do you think? That when they are saying low pressure regime, is volume is large. You have to provide the larger volume at the exit. So what do you think? These molecules are close to each other or far from? Far from each other or close to each other relatively in low pressure regime?
Far
from each other. So when they are far from each other, okay. Now tell me that if you take two molecules, there is something called electron cloud. Okay. So basically, when two molecules come closer to each other, after a certain distance, what happens? The force becomes repulsive or interactive. What do you think? If they are very close, that is called hard sphere. That after that they cannot penetrate. What do you think? Repulsive. And after a certain distance, forces become attractive. So that's how this curve looks like. If you see this interaction energy curve, it's like this. Okay, so this is molecular P. Molecular P. And this is distance, let's say. Distance, molecular distance. Okay, so if you are in low pressure regime, okay, so where forces are attractive and where forces are repulsive? So you know that attractive means potential energy should be negative. If you remember your electrostatic chapter, when the charges have opposite sign, then they attract each other, and the electrostatic potential energy becomes equal to that minus Q1 Q2 by R square, and that constant 1 by 4 pi epsilon naught. Okay, so whenever you have attraction, your potential energy is negative, which is this one. If I am wrong, you can correct me, because you are fresh than, you are more fresh than me in terms of these concepts. But I think I am right. Is it fine, Bhavna? Am I right?
Yes, sir.
Yeah, so this zone is attractive forces dominate. And in this zone, repulsive forces. So when you are in low pressure regime, here you said that the molecular distance is relatively larger. Means if larger, then which forces dominate? Attractive or repulsive? Bhavna?
Sir, your voice broke. Can you just repeat once?
I said that when we are in low pressure regime, Okay. Then molecular distance is larger. That's what you said. Molecules are far from each other, right? Relatively.
Yes, sir.
So which one will dominate? Attractive forces or repulsive?
When distance is larger, attractive forces will dominate.
Yeah. So in low pressure regime, attractive forces dominate. Attractive forces dominate. Now we said that there is no work transfer. There is no heat transfer. So whatever gas has to do, gas has to play with its own energy. So when attractive forces dominate and gas is trying to expand, gas has to extract energy from itself, or energy will be really, what do you think? Right? Gas has to overcome this attractive force, right? Means the molecules in order to expand, right?
Yes, sir.
Yes.
So it means if gas will extract the energy, from where that energy will come? What we are saying that you have to overcome this attractive, what we call this molecular potential energy, molecular P, which is attractive in nature. Its sign is negative in this low pressure regime. We are here. So in order to from where that energy comes, because gas has to expand, you are forcing the gas that expand, because as I said in Joule-Thomson, P exit is always less than P. So you are forcing the gas to expand. That's why you are controlling P exit. If you are forcing the gas to expand, then the gas has to overcome attractive potential energy, and in that will be compensated. Gas will extract energy from this molecular K, and once you extract, the gas will take that energy from molecular K part, temperature will go down. So T exit will go down. Is it clear? That's why gas shows cooling effect. And if you go to high pressure regime, high pressure means volume is smaller, means you are pressurizing the gas at exit, you are maintaining a bit higher pressure. What will happen? When you are maintaining the very high pressure, the molecular distances becomes very small. So small that, so small that repulsive, right? Is it correct? That now molecules are coming so closer that repulsive forces dominate. Once you have repulsive forces, then gas will automatically expand because molecules will try to repel each other. So due to that repulsive, so it's basically that when same charges of same sign come closer to each other, if you don't fix them, they will go apart because you have positive potential energy. So due to that positive potential energy, some part will be used to expand the gas and some part will add into this molecular K here. That P will get added to this K. So whatever, so when this gas will repel, this energy will be released in the sense that so that repulsive energy will be sufficient enough to expand the gas as well as to add some extra in this molecular K, and hence temperature increases. I think it should be convincing for you guys. Your comments. That's what I wanted to explain. Molecular through the molecular interpretation. Mathematically, I still haven't answered. I acknowledge. We will come back because we don't have sufficient tools. We need some more mathematical derivations. Is it clear?
Yes, sir.
Yeah. With this picture now, so I thought that I must elaborate on this experiment because this is something new for you. After that, again, life will be easy because now we'll solve the problem, not very difficult. This topic was very important. That's why I took time. Okay. Tomorrow we'll solve only problems. And this way we will wrap up this first law of thermodynamics and then we'll quickly shift to second law. So probably from Friday we are going to shift to second law. Tomorrow we'll do only problems, nothing else. Thank you guys. Today's class was really helpful for me because your input was really good. Because when many doubts were coming, sometimes I was also getting confused that whether I have read the experiment correctly or not.
Sir?
Yeah, please come.
Sir, could you please explain again the high pressure regime? Why the temperature?
So see, when you say high pressure, don't you think that when you pressurize the gas a lot, basically molecules are coming closer to each other?
Yes, sir.
So when molecules are coming closer to each other, means distance is decreasing.
Yes.
They decrease so much that rather than attractive in nature, the interaction becomes repulsive, right?
Okay. Yeah.
So if two molecules are repelling each other, they will automatically expand, and you will get some extra energy also. It's like you remember you do the classical problem that two charges are fixed. Probably during JE you have solved it. Two
Yes, sir.
are fixed, and then when you remove those fixed, if you don't hold, then they will move, and it has been asked that what will be their final kinetic energy, something like this, right? So the
Yes, sir.
repulsive energy gets converted into kinetic energy, something like this is happening here. Okay. So that is the molecular interpretation of Joule-Thomson effect. You understood cooling, heating. We want cooling, okay? We don't want heating effect, and this has a huge application. I promise that I'll try to explain you mathematically also when we will be in a position to derive this expression, because I also have to work out to give you the complete mathematical answer that why H remain constant. And as we said, everything, the main information is V, and V is related to beta. So we roughly answered it, but more precise answer, we'll do it when we'll come to the chapter of thermal potentials. Thank you for your extra time, batch. So let's meet tomorrow. We'll solve questions. Thanks.
Sir,
Yeah, please.
So, tomorrow the maths teachers are taking class tomorrow also.
Oh, okay. So again, we go to Saturday or any other day you want to speak? Or it's fine. Saturday it's fine.